In this stoichiometry problem, we're going to examine limiting reagents. So let's look at what the reaction is going to be for us. So we're asked to come up with the recipe, the balanced chemical equation, and in this situation they're actually going to provide the skeleton equation to us, and here you see it's here it is. So we're going to go ahead and balance the equation. How did I get these numbers? I saw that I needed 2 irons on the left side. I had 2 on the right side, so that's why I put a 2 out in front of the FeS2 on the left side. Then I took care of the sulfur, putting that 2 forced not only 2 irons but also 4 sulfur, so that's why on the right side I put a 4 in front of the sulfur dioxide. Then I added up all of my oxygens on the right side. 4 times 2 is 8, plus 3 is 11. That's why I put 11 halves. And as always, we don't want fractional coefficients. So I'm going to go through and I'm going to multiply by 2. And so my ratio is 4 to 11 to 2 to 8. So there's my recipe. Remember, these are molar ratios. So let's look at what we're provided in this reaction. So this is a little different now. We've got amounts for both reactants, 195 grams of ferrous sulfide and also 165 grams of oxygen. I got to figure out which one of those is going to run out first. So let's deal with the FeS2. I've got to get that to moles because, again, my balanced equation involves molar ratios. So I divide by its molar mass. And then I look at the entire equation as a batch. And when you look at the entire equation, to produce one whole batch requires 4 FeS2s, 4 moles. And so when I do this calculation, I figure that I'm going to get a little over 0.4 batches. Now I go to my second reactant, the oxygen, following the same idea. I've got to get that to moles first. Remember, oxygen is diatomic. I divide by 32. Again, the entire equation represents a batch, and the coefficient out in front of oxygen is 11. So I need 11 moles of oxygen for a single batch. That's why I got 11 moles in the denominator. I do my math, and I get 0.468 batches. Again, the one that gives me fewer batches will run out first, and that, of course, makes FeS2 my limiting reagent. Now, in part C, I need to take that information and utilize it as I'm asked to find the theoretical yield of the ferric oxide. So you want to start with the limiting reagent. He's the one that as soon as he runs out, I won't get any more ferric oxide. So I've got to start with the 195 grams of FeS2. The ratio between FeS2 and ferric oxide is 4 to 2 or 2 to 4. That's a molar ratio. I have to get this to moles. I do that by dividing by its molar mass. Now I can use my ratio, and obviously I'm getting fewer moles of ferric oxide than moles of FeS2 that are being consumed. And finally, usually theoretical yield, if they don't specify, that means they want it in grams. To get from moles to grams, I'm going to multiply by its molar mass, which is 159.70. I do the math, and I'm predicting I'm going to get 130 grams of ferric oxide. That is the theoretical yield. So limiting reagents, just like with the recipe problems, when an ingredient runs out, it determines how much product could possibly be produced.